Electric current is a flow of electric charge. Now, electrons generally are the ones that move this charge around, and it's usually through a conductor such as a wire. The SI unit for current is going to be the ampere, and the symbol for current is going to be I. So that's the symbol for current, and then the unit is going to be an amp. Okay. We traditionally define it as I, average, is the change in charge over the change in T. It could also, of course, be just Q over T. And some books have capital T, some have lowercase t. I'm going to most likely use lowercase t, but I'm just showing you based on what most books have. So let's start with A. A wire carries a current of 1.6 amps. Let's identify what they've given us. And they want this per second, so time is going to be 1 second. We're going to first find the charge Q that this wire is carrying. We solve for Q, plug in the appropriate numbers. This ends up giving us, if we show the units, this is 1.6 amp. An amp is a coulomb per second. So what we see here is that these seconds cancel out, leaving us with the charge of 1.6 coulombs. However, the problem is asking for us to find the number of electrons that are passing through. So with that in mind, we're going to take the charge and divide it by the elementary charge. You'll notice that the coulombs cancel out. And if we plug this in the calculator, we're going to get 1 times 10 to the 19 electrons. Okay, now we're not going to do this for every problem, but in this particular problem, they were looking for the number of electrons. And that's what we do. If all we were doing was looking for the charge, then we would have been done with the problem at 1.6 coulombs. Here's a more straightforward problem. We have a current of 0.835 amps and a charge of 1.67 coulombs. We want to find out how much time it takes to do this. So, of course, we have I is equal to Q over T. Solving for T, we get Q over I. Problem 2 is quite fascinating. Be careful, you might have to go back and rewatch this a few times. What we have here is we have a series of wires representing a circuit, and where the wires meet are called junctions. So for example, we have these junctions right here. Only these are junctions. Junctions are a part of a circuit where you have to make a decision which way you want to go. It's almost like a maze. So for example, you have these 5 amps going in to this junction right here. And when it hits this junction, these 5 amps must allocate themselves in one direction or another direction. So for example, we have 5 coming into the right, and then there's 2 amps going up. Some of it, the rest of it is going to be going forward in this direction. In this case, we're looking at 3 amps because 2 and 3 combined to give me 5. So there's definitely a conservation of charge here, or conservation of current, if you will. Okay. So we know that going into this junction where we have I, that is 3 amps. Looking to the right of this circuit, so we're concerned about finding out what this value of I is going to be. Looking to the right of this circuit from this junction point, we have 4 amps going down into the circuit. We have 3, even though it's drawn interestingly, this is just one straight wire. There's no junction at this corner. Okay, so there's no splitting going on. But we do have this 2 amp branch that's coming into this junction right here. So consider for a moment that if 2 amps are going in here, and then there's 3 amps going to the right, that means it must have gained an extra amp. So going to the right, we have 3 amps. Okay, and that's because the 2 met up with 1 at this junction. So the 1 going into this point right here, and the 2 going into this point right here, ends up giving us 3 going out this way, and therefore going upwards as well. Now, this 1 amp must have come from this 4 amp that split at this point. So to the right, I have 1 amp from the 4. To the left, I will have another 3 amps. Now that all of this has been solved, we have the 3 amp and the 3 amp combined at this junction point right here to give us a total of 6 amps. And these 6 amps are going to be going in a direction downward. Summary, how are charge and current different? How are they related? Think about that. So when it comes to current, we do have two forms of current. We have alternating current and we have direct current. Direct current, of course, was the first of the two that was better understood, and this is courtesy of Alessandro Volta, who created the voltaic pile, the first battery. Of course, Alessandro Volta based his work on Luigi Galvani and the seminal work on frogs, of course, and copper and zinc pincers. Okay. Now, the assumption that current goes from positive to negative, which we're going to also do here for direct current, was first considered by André Marie Ampère. Of course, we named the current after Ampere, right? The unit of current is ampere or amp. Direct current flows in one direction, okay? We're going to assume that, and we're going to assume that it goes from positive to negative. Alternating current periodically reverses direction. So there is a reversal, and the important word here is period. Period is in nature and in math and in science is where we have a cycle that repeats itself. Okay. Here we have two graphs, graph A and graph B. The question is going to be which graph has a higher magnitude current. So to do that, I'm going to do some slopes. Graph A, I'm going to go ahead and pick a couple of points. I'm going to pick a point right here, for example, and I'm going to pick a point right here. Do we always do slopes? Again, we do this be looking at the rise over run, right? We have a charge and we have a time. And if we do Q over time, by definition, that is the current. So in this case, I am doing the slope because that'll give me the current. Let's see, this is going to be 1, 7. This will be 3, 11. And if I go ahead and do my rise over run, it's 11 coulombs, 7 coulombs, 3 seconds, 1 second. I get 4 coulombs over 2 seconds, and that is 2 amps. So for graph A, I'm looking at 2 amps. For graph B, if we repeat the same process, again, you pick any 2 points that you feel comfortable with. I'm going to do 0, 2, and I'm going to do 1, 4. I have 4 coulombs minus 2 coulombs over 1 second minus 0 seconds. I also get 2 amps. So folks, they carry the same current. They carry the same current. And of course, in other words, they carry the same current or the same flow of electrons. Let's talk about what these things look like. So, for example, I'm going to call this x-axis time. This is going to be alternating current. This is going to be direct current. And for direct current, I just have a straight line. And of course, this straight line is going to be a magnitude. Because it could be positive x or it could be in a positive y or the negative y, but we're going to just do magnitude. We're going to do absolute value. It has a strength. Okay? So direct current looks like this, just straight. Okay? Alternating current, on the other hand, looks like this. All right? And this is pretty important. This is alternating current, and this is called a sine wave. And this is from trigonometry. Okay? And the idea here is that it is periodic, right? Periodic means that it repeats. So technically, this wave would keep going, right? It would keep going like so. Oops. And keep repeating, right? And doing that kind of a behavior. Now, what's happening here is, for example, in this positive realm, we have electrons that might be going in this direction. But then on the second half, we have the same electrons, but they're going in the opposite direction. So alternating definitely means that they are going back and forth, okay? They are going back and forth. So the electrons move in one direction here, and then they move in the opposite direction here, and then they go ahead and switch again. Okay, so they are definitely switching directions. It's the same magnitude strength, quote unquote, but you have the directions that are changing. And that's what makes it different from direct current. I want you to go find out more about some electrical components called a rectifier and an inverter. What do they do? Explain what happens when you plug your cell phone to a charger into the wall. So, for example, what kind of electricity do we have behind the wall? What is the charging box doing, right? What does the wire carry into your phone? What kind of electricity or what kind of a current does your phone require? What kind of device is holding that current?